Hi everybody, this is Dr. Pingle. It's Tuesday the 16th, 17th, something like that. 17th. I'm doing a quick lab report here just to document some of the work I've been doing over the last week and a half or so. Some news. This is a nice article that I ran into from Niantic. They created some of the first big AR, augmented reality games, talking about Gaussian splatting. Nice page that sort of details how it works, and I'll link this on the wiki. This is a release by Jeff Boeing of OSMNX2. I haven't tried it out yet, but I talk about OSMNX version 1 whatever in cartography and geovisualization. Pretty cool Python software for generating these sort of like Noli style figure ground maps. The prototype of the lab t-shirt is in. I ordered one of these just to sort of see if I sort of liked how it came out. I think it came out great, so we'll go ahead and order these shortly. This is a project that Liam is going to be working on, and I'm sort of working on by proxy, doing some LiDAR scanning down in Peru. I just wanted to document the page. We got word from Ridge Waddell that ArcGIS Indoors is turned on. Sounds like Kevin got this installed and should be ready to go. So excited to move forward on that in the spring semester with Lily. This was kind of a neat one. So we've got ArcGIS Reality. Carl Lippo has this. So we've got it installed on the big research machine in the lab. So I haven't tried this out yet, but it looks like we've got a mechanism here for taking just paid satellite photos and turning those into 3D. I haven't tried this yet. Who knows how well it works, but pretty cool possibilities. I wanted to sort of re-bring this to the lab's attention. So I think Jack Gonzalez actually found this way back when, but this is a program, the National Center for Airborne Laser Mapping, NCALM, where students can apply for little mini grants to get specific sites imaged. Pretty great. Open Topography announced some new tools. So this is some cloud-based processing. I don't particularly have any interest in this, but it's nice to know that it's out there. Okay, and then I did some adventures in point to mesh. This is part of a larger effort to try to turn point clouds into meshes. Paul from the ETS had found this. This is a deep learning based approach, actually, fairly old, so 4 years old, not a lot of updates since then. That's a little bit of an eternity. I tried to get this working. I didn't have a lot of luck, so I'm trying to document here some of the things that I did try. I tried it using it sort of, let's call it native settings. With NumPy 118, kind of an old version of PyTorch 3D. It did install, sorry, the older version did install. The YAML file method didn't install. I suppose I didn't try it on a straight Linux machine, so I could try that. But also tried some newer versions. Got some NumPy errors. Some things had changed in terms of how the function calls get made, but nothing worked. So anyway, I ended up giving up. The last error that I got was this: unable to find a valid CU, I guess that's CUDA DNN algorithm to run the convolution. A little bit of what that looked like. Yeah, got, a ways. I guess I spent probably about 2 hours on this. Sad to not get it finished. One of the problems that I ended up having was, it really wasn't accessing my GPU properly, kind of no matter what I was trying. So, yeah, strange. Yeah, documenting some more. some more attempts. There's a couple of re-implementations of this. I didn't really get anywhere with those either. I found this while I was looking around. So this is more point cloud to GPU, point cloud to mesh processing software. This is GeoMagick Wrap. I stuck the big point cloud into this to do it, and it just kind of ran and did nothing for several days. I think I've got like a 2-week trial. I may take another run at this, but so far no good. I did, one of the cool things about the previous software, not the GeoMagick Wrap, but the point cloud to mesh, was that it had some supplied meshes. I don't know how standard these are. I guess in retrospect they probably are pretty standard, but one of these was just a giraffe, and just did the Poisson reconstruction and cloud compare, and that worked great. You know, as good as you could possibly imagine. So you know, it's a little frustrating that, you know, regular environmental scan point clouds don't do this at all. It is not anywhere near this easy to get these things done. So I think it will be a challenge. I went back and sort of followed the instructions that I had created many years ago now. I don't know how old these are. I mean, the date on this is 2022, but that was the last time that, what's his name? Chandler and I took a look at this, and sort of got, you know, a ways into this. The instructions for this are actually from 2019. Probably earlier than that, even 2018. Anyway, nothing worked, and that's a little harsh. Okay, nothing worked. I got pretty far. So you know, resampling the point cloud worked. Calculating the normals seemed to have worked. It had the same sort of problems as I had at NIU, so Zulauf and Holmes, at the NIU data set sort of had this weird, you know, the normals were inverted. So same sort of things happened with the tall buildings on the Binghamton campus, and had to sort of carve those out and invert them, and that all worked just fine. I went through some tests on the Poisson surface reconstruction. I don't know how many of those I have documented in here, but yeah, just sort of you know, exploring this. What didn't work was sort of steps 7 and 8, trying to create this thickness to create a solid model just didn't work. I did spend a ton of time on the Ouster. This kind of got started off via the Ouster SDK webinar. So I attended this, I guess, last, I don't know, Thursday. They're talking about, they had a couple of different things that they did, but the bulk of it was focused on this Ouster CLI command line interface, and then the Python interface. The Ouster CLI interface was great. I sort of learned a lot, just sort of the philosophy of it. And the gist is you sort of use this Ouster-CLI, which installs great, like no problems at all getting it going. So that's kind of a testament to the quality of it. You know, you define a source. This can be a file, or this can be the IP address of the instrument itself. You can configure things. So in this case, I was trying out setting it to send to multiple destinations, which looked like it was supported in the documentation. Didn't actually work, but cool that you can update configuration this way. I put a couple of these out here. Sort of the standard way to do this would be to call Ouster CLI, define the source as your IP address. You can visualize, which is kind of nice to sort of see things as they come in, and then you can just save all of that data back out as a PCAP. So you don't need Ouster Studio to save things anymore. You don't need Wireshark. You can use the Ouster CLI to just log things directly, which is great. You can also save things directly to their OSF, which they both called Open Sensor Format and Ouster Sensor Format, which was kind of funny. I suspect it's probably better to save out the PCAP and then translate it after the fact. But you know, if you're dealing with a device that is maybe on the small side, you know, not terrible to be able to do OSF. You can do things like, say, clip. So basically, you're sort of piping these things one into another. You can clip things to get rid of nearby points, which is kind of nice. You can do things like accumulate every certain number of meters. They have it by frame, but actually the meters is kind of even better, because as you're doing SLAM, you don't need a new overlay every, what if you're paused? What if you're waiting? Just do it by distance. So anyway, that was pretty great. This is an example of what some of the clip things can do, some min range, max range. It can do it by percentile, which is pretty cool. There was a benchmarking tool that I found, so Ouster CLI util benchmark sensor. This was great. You could get a sense to see that all of the packets are coming in. I thought I was dropping packets, but it turns out that they're just sort of showing up out of order, which is great. I mean, it's not great that they're showing up out of order, but it's great that they're not getting dropped. And easy to reprocess those back, I think, and figure out where they're supposed to go. So I think this is one of the great things about sort of storing in PCAP and then writing back out again to OSF, is sort of just writing the wire down as it comes in, and then fixing things later. The next bit of it was on the Python portion. This was run by Tom Slenkard. He seemed to really know his stuff. There was a lot of really good examples here. Hard to follow, but he said that all of the stuff was going to be, I think he said he hoped all the stuff would be available after some of it was going to get posted to the community forum, which I think I put a reference to earlier. But some really cool stuff like brushing, sort of comparing the 2D view to the 3D view. He had this de-stagger mode that really cleaned up the image quite a bit. I didn't catch all of it, other than that the data is staggered for some reason, and you kind of have to unstagger it. I don't know why you do that, but I'm sure they have a reason. Yeah, really, really useful stuff here. They talked about the release of Ouster Studio Web, which I think they had said it happened like the day before. I think I had actually happened upon this maybe a week earlier. But this is basically a cloud-based visualization of your data, of sample data that they've got. Pretty handy to have that stuff. One of the things that I don't understand is, the blockiness of the images isn't so hard to understand. It's essentially, part of this is like artifacting and, not a super dense image, all things considered. Mine doesn't look as good, and I don't know if that's partly because something is misconfigured or what, but that the 2D kind of style, mine doesn't look as good as that. This was an example of a full data acquisition. So I think in the previous lab report, I had documented one good mini SLAM of basically my office. And so I extended this out, recorded it with the Ouster CLI, wrote the data out, and then read it back in, and did this sort of real-time SLAM with it. Maybe not quite, well, real-time enough. One of the cool things about this is the slice command. So oftentimes as you're getting ready to start a scan, there's stuff as you're sort of putting the computer in or doing whatever you're going to do. So this let you, could visualize the thing and figure out where the scan really kind of started, and then plug it back in. So here I'm saying slice 475 colon, just like Python syntax. So that's 475 on to the end. You could trim that. I haven't tried a negative number here. I actually assume it probably would work since it's all based on Python, but I don't really know that. I've got the map here, adding an accumulation frame every meter to kind of keep the file size reasonable. I suppose you could save every little last bit of it if you wanted to, which might be pretty cool for some of the indoor mapping. I really found the trajectory of this to be quite good, and you can by the way save this at the end. So there's a just tag save.whatever.last on the end of it. The quality of this is really fantastic. I'll show on the next slide Well, okay, so this is a little bit of sort of chaining some stuff together. You can always do dash dash help at the end if you're not quite sure what you want to do. In this case, you're invoking the command line, you're defining your source, you're slicing it, you're running slam, you're visualizing the result of the slam, you're saying that you want to see a map of it, you're accumulating a frame every 1 meter, and then you're saving that back out again, and you're sort of asking how you want to save it. And you can do things like say, well, I want the resolution of my data to be 0.1 meters or 0.01 meters or whatever it is that you want. Set the max Z, set the max min Z, stuff like that. Anyway, really, really flexible. I'm digging the Ouster CLI. The only thing that I'm not super thrilled about, and I guess I'll got a slide on this in a second, is the kind of limited SLAM options. When you're running SLAM, you can define things like the voxel size. I don't know that this is how it's written out. For instance, you could slam it sort of in this sort of voxely way, but then keep all of the points as they really were. Or maybe it's just outputting the state of the voxel. I don't know. I guess you could figure that out by looking at the data and sort of seeing how much variability there is at that scale. So I don't know, question for the future, I suppose, but it doesn't really matter. This is an example of what that frame looked like. I was really pretty happy with this. So this is like an interior scan, looking from the outside, looking in. Lots of information here. One of the things that I will say is, there's no loop closure here, which means that it doesn't have the ability to sort of reassociate old key points with new key points, which means as you're moving through the environment, it doesn't really tie things together neatly. In this case, there's some bad stuff as I kind of walked through the house and come back through. Things don't really line up quite right anymore. So the beginning part of the scan is pretty solid. Actually, it's pretty solid almost all the way to the end. So I don't know if there was a rotation or something. You could actually totally easily trim that out by just not including the back part of the scan. Yeah, other ways to clean that up, I don't know. Plus, you've got sort of every possibility to sort of feed this through a different SLAM algorithm, and that's kind of one of the next things that I want to look at is feeding this through interactive SLAM or whatever it is that came after that. I think that there are more powerful ways of processing this data, but I feel pretty good that we're actually collecting it, which is great. The physical setup looks something like this. I had a battery powering the LiDAR. I played around with both using like a drone LiPo battery and a personal power supply. I played around with lots of different ways to log it. I did try the packet squirrel. It seems like it dropped frames, although I would like to maybe go back and look at that now that I know a little bit more about it. It could be that stuff was just logged in a different order and everything is intact. If that's the case, then we've got a really easy, small, portable system. If we have to have a laptop, it's not so bad. But I think it would be pretty great if this could be all, on a Ronin. I did test the DJI Ronin. I didn't do a sample collection with it. I'd really like to turn the yaw correction off, I think, or maybe have it soften it. I don't know. Essentially it tries to keep the thing pointed in the same direction all the time, which is okay. It just makes for a, how do I put this? You'd have to pay attention to the orientation that you're traveling in all the time to make sure that it didn't get off, because like the cord is basically going to point north all the time. So yeah, I don't think that's great. So probably best to turn that off. I guess the next place I'd like to take this is to, there's an updated version of Interactive SLAM called GLIM. I don't even know what that stands for. It's probably on this page somewhere. But it seems, I don't know, why did I think that this can do I think that this can do Ouster without any problem. There shouldn't really be any reason why it can't. But this would be sort of the next step, is to try this out. I also want to try out the Ouster in sort of like a, outdoor setting. I guess I've only done it indoors, so outdoor, like around the house, through a forest. I have no idea what its capabilities are with its included. The SLAM algorithm is KISS. I don't have any idea how good it would do with that stuff. I think for small scans it works great. My concern is that if you try to do this at the building scale, you're going to wind up with problems. And maybe the thing to do there is to like do some scans and then divide your scan up into pieces and assemble them. I don't know. It definitely seems pretty good on the short run. I don't know how you assemble those things. Okay, so some more stuff on 3D printing. This is actually kind of going back to some of the stuff I talked about earlier. I spent a lot of time on this. Some notes here. I think most of these are pretty solid. I don't know. I did a little bit of testing. I don't know whether it's better to sample it at 0.1 meters, for instance, instead of 0.25. Yeah, we'll leave these notes just kind of the way they are. This is the result. I thought this is great. If I could get this thing to print, I'd be super happy with it. The only problem is that this is essentially like a 2D face structure and it doesn't have any depth to it. And I'm not quite sure what the easy way around this is. I've looked at a couple things. I guess I've got a few slides on this here. I tried following the instructions and creating a ground surface below it. That was easy to do, but I couldn't get it to wrap the whole thing around it like I could for some reason with the NIU data. Yeah, so I don't have any really good reason why that's not working. It's a good idea. Basically, you take the existing point cloud, you define, set all the z values to 0, and then raise them up to wherever you want it. And then the idea is to run a Poisson surface reconstruction, and it's supposed to wrap the whole thing around, sort of like the shrink wrap. But it totally doesn't do it. It does each one separately. I think that there's just too much terrain here. I think at NIU is super flat, and so the distance between the base and the top was only ever some meters, and here it's like dozens or probably, I don't know, maybe it's probably not 100-meter difference, but it's big. And yeah, I just can't get it to go. Yeah, what could I do? Yep, not a great idea here. You'd almost need to set, sort of thinking out loud here, but do a ground filter stage, and then you could put the points just under that until you get down to the base. Then it'd be sort of cloudy enough, so to speak, that it would probably wrap. That's a pretty good idea. I don't know if I'm going to have time to try it out, but that should probably work. The big danger is like making sure, like once you get below the ground, you can do whatever you want, but on any buildings with overhangs, you can't just extend it straight down. Otherwise, you just wind up with sort of like a DSM mesh, which we're desperately trying to avoid. But I suspect you probably could do the ground layer and then just put it below that. I don't know. It probably wouldn't take long to try. I should try. Okay. Talk myself into it. One of the things I discovered along the way is Autodesk has a couple of tools. So I did try some of these. I didn't get very far, but Autodesk 360 has some tools for repairing a mesh body. This would be a great thing to try. In fact, this is another, if I had all the time in the world, I guess I would just try this today. We'll see. There's also Recap Pro, which is point cloud-based software from Autodesk. It's got a scan to mesh tool, but it requires credits. It seems pretty pricey, so I don't think we're going to try it. I did download it and load it. This is what it looks like. There's your scan to mesh. Importing that mesh, this is a ton of points. This is a ton of vertices. It ran. I never got a good look at it. There's like 4 different like repair tools in it. Yeah, none of these. I don't know. I got to try it on like a smaller sample, I think. Yeah, then this is kind of going back to the cloud compare thing. I couldn't get it to wrap around. Although this ground thing, that's a good idea. I think I'll try it. Okay, and then the last thing that I worked on is YOLO 5. This is, Sharif has been working on this. Shashank used this as part of the build stuff, and I never ran it. Sort of, got the reports from Shashank and heard about how it all ran and talked to them about it. So I think the theoretical understanding was there, but actually executing it, I hadn't tried. So I got really far with this object detection in 10 minutes by this guy. He walked through the whole setup. Where you get it, there's a Ultralytics is the sort of definitive repository for it. So if you go to Ultralytics, and I'm using YOLO 5, and I forget what they said now. They're on 11. So I haven't tried 11, but it was fine just to sort of get progress through 5. When you install it, there's a sort of basically a pip install instruction that is pretty straightforward. It worked for using the webcam, and it worked for using the CPU for this stuff, but it didn't work on the GPU training, and it didn't work when I was trying to extend it out. So I ended up having to install a Conda environment. I mean, both of them were Conda environments, but using Conda to install the packages as shown here. I created a wiki page for YOLO, which is not at this address anymore, actually. It's not at YOLO v5. It's just you only look once, something. If you just put in YOLO, you'll find it. One of the cool things is, so you set up the packages, you activate it, you go to that directory, and then you can get kind of off to the races really quickly by Python train PI and then pointing it to your data. So it's supposed to be 2 dashes, dash data, and then point it to a YAML file. And this YAML file contains sort of where the images and whatnot are supposed to go. This one comes with the YOLO v5 install, and it has a download link at the bottom of the YAML file. And so it will just automatically go and download the data and run everything. So really kind of awesomely automated. And it works. So basically, I went through and ran it on the test data, watched another video on running your own data. So downloaded this chess data set that was linked on the YOLO, I don't know, custom data, whatever. And it was really easy. So Python trained it on the data set. Device 0 just means to use my GPU. I only have one. And of course things start at 0, so that's that. I could then take that run and apply the model to the webcam as it's loading stuff in, and it is automatically detecting these chess pieces according to it. Now it's not doing a great job here, and that's fine because it's super, like, these aren't the chess pieces that it trained on, and whatever, but I'm still impressed that it does even this well. When you run the stuff, it's going to save everything to its like YOLO 5. I think there's like a runs directory, and then it just saves everything. Excuse me. Just saves everything there. The Cocoa dataset is huge. I didn't even try to run this. I think would have taken days. But if you run it on Cocoa 128, it's like 1% of the data. That actually ran in 10 minutes. So it was a great way to get started. And then the last thing that I played around with was tagging. So essentially, this is the whole window of like installing it, running, uh, running it, training one, and then running it. And then this is tagging your own data. So I used the chess data, but I tagged it myself. And here I'm using, oh, maybe I get rid of the, is this the Microsoft one? This is not the Microsoft one. So I tried Microsoft VOTT. It tags things fine. It doesn't save it in YOLO v5 format, which I didn't like. So this is Label Image, which is kind of an older version. Now they have Label Studio, which can handle more different types of input. This is for images, but wow, is this fast on images. There's a couple of key things. One is that you need to define a classes.txt file. It just is a list of all of the labels, just line by line. When you load it, you've got to make sure you're in YOLO mode. These have keyboard shortcuts for everything, so it's Control Y. But if you just like hit where it says that, where the arrow says YOLO, you can sort of toggle through different kinds of output formats, changing your save directory. I think I invoked this one with what should have been a save directory, but it didn't take. It was easy enough to move those. What it does here is it just generates a text file that sort of shows where all of the classes are and whatnot in your image. But yeah, you can just plow through these labeling tasks. A, S, D, and W. I guess just A, W, and D do most of the work. You can set it to autosave. In this case, I had it set to a single class, so I could just sort of rip through and do all of the white kings, which is all I did here. You could label every chess piece if you wanted to, but I was just trying to get a sense of it. So fast. I mean, I don't know how many you could look at. You must be able to look at well over 50 frames a minute, maybe approaching 100 frames a minute. Yeah, you could get really fast at this. So I liked this a lot. I think if Shashank could use this for the instead of VOTT, he would have saved himself some trouble. Unfortunately, annotating the stuff is one of the worst parts of the job, and this makes it really easy. And you can zoom. So VOTT didn't let you zoom, but this one does. Just like exactly what you need to label things fast. All right, so not a formal goal set here, but just to have something, sort of just taking on as many small tasks as I can. I think based on what I've talked about here, just going back to those meshes and seeing if there's anything I can do to add some thickness to those. I'd gotten away from that. I got to finish my objectivity paper. I should probably do that tonight. And then I can move on to working on Addison's paper. There's actually a couple of other things I've got to do for Solomon's work as well, which didn't make this list, but just a ton of little things. So keeping at it. Break is a good time to get a bunch of work done. If it's your time to relax, I hope that you do. But I enjoy having these big blocks of time to work with. And yeah, miss it. All right, see you.